Bismillahirrahmanirrahim. Assalamu alaikum. So today we will start the second portion of plasticity, in which we mainly discuss the failure theories. In the previous video, we have discussed the basic theory of plasticity, and different material models and different flow rules were discussed. Okay, so today we will try to discuss the failure theories. All engineering materials are classified as ductile or brittle material. Okay, generally a ductile material is one in which gross plastic deformation is greater than 5%, while brittle material having plastic deformation less than 5%. Means ductile material has more deformation as compared to brittle materials. Ductile materials show large plastic deformation and observed necking prior to fracture, but on the other hand, brittle materials fails suddenly without proper indication. Okay, we know these two properties of ductile and brittle materials. Okay, ductile material will show a huge plastic deformation before fracture, but brittle materials does not show any sign of failure, and then it fracture immediately when it reaches the maximum load. Both materials behave in different manner, hence they have different failure criteria. So the failure criteria for defining ductile and brittle materials, we have different theories that defines the failure. One single theory cannot be used to predict failure in both the materials. Permanent deformation in ductile material is observed when load reaches the yield point. So after yield point, we have plastic deformation started. So for ductile material, the failure point is yield point. Any further load will strain harden the material. Okay, so if we increase the load beyond the yield point, and so we have the permanent deformation inside the material. In brittle materials, yield point is not clear, that is determined by offset method, and fracture usually occurs near to ultimate tensile strength, that is UTS point. Okay, so for the brittle material we apply load and it fracture at the um, maximum load point, that is generally a UTS. Okay, hence for ductile material failure criteria is based on yield strength, while for brittle materials failure criteria is based on ultimate tensile strength. Now, following section will discuss different failure theories for ductile as well as brittle materials. Now, failure theories for ductile materials. As discussed earlier, that for ductile materials, failure is initiated when material reaches the yield point. Also, all failure theories are formulated by considering principal values of stresses or strains. So, the 2 points are that we have yield point as a failure limit, and we consider the values of principal stresses or strains to exemplify the failure in ductile materials. So the first theory is maximum shear stress theory. It is also known as Tresca criteria. It states that yielding begins when maximum shear stress at a point reaches the maximum shear stress at yield under uniaxial tension or compression. So it simply says that failure will start or yielding will start when the material reaches the maximum shear stress point. Okay, so below that there will be no failure. Okay, for multi-axial state of stress, shear stress is obtained by, we know that tau 1 is sigma 1 minus sigma 2 divided by 2, that is the radius of the Morse circle. Tau 2, that is sigma 2 minus sigma 3 divided by 2. Tau 3, that is sigma 3 minus sigma 1 divided by 2. Okay, so maximum shear stress is the largest if sigma 1 is greater than sigma 2 is greater than sigma 3. Then we have tau max equal to sigma 3 minus sigma 1. Okay, that is the radius of the largest circle. Okay, so tau max will be sigma 3 minus sigma 1 divided by 2, or sigma max minus sigma min, or sigma max min minus sigma max at the absolute value. Okay, So I hope you understand the maximum shear stress and how we calculate that. Okay, we have discussed that in the chapter of stress in detail. Now consider an element from uniaxial tension subjected to yield. So we have a uniaxial tension. So means one of the normal stress will be equal to yield. So sigma xx is equal to yield, and all other stresses, that is sigma yy, sigma zz, tau xy, tau yz, and tau z is equal to 0 because it is uniaxial tension case. Okay. So now using Mohr circle equation, that is sigma 1 comma 2, those are the principal stresses, can be calculated in terms of the sigma xx, that is sigma xx upon 2 plus minus root sigma xx upon 2 whole square plus tau xy square. This Mohr circle equation is simplified for uniaxial tension. So by replacing this, the value of sigma xx is equal to sigma y, and after simplification what we get, sigma y upon 2 plus minus sigma y upon 2. So sigma 1 is equal to sigma y and sigma 2 is equal to 0. Okay. So for uniaxial tension case, the stress sigma 1 is equal to sigma y and sigma 2 is equal to 0. So maximum shear stress gives tau max is equal to sigma 1 minus sigma 2 divided by 2. That is sigma y minus 0 divided by 2. So tau max will be sigma y by 2. Okay. If the principal stresses are unordered, yielding under multi-axial state of stress occurs for any of the following conditions. Unordered means generally we took sigma 1 is greater than sigma 2 is greater than sigma 3. But if we have unordered, means sigma 1 can be smaller, sigma 3 can be greater, or sigma 2 can be greater. So in that scenario, we have these three options, that sigma 1 minus sigma 2 can be plus minus sigma y, sigma 2 minus sigma 3 can be plus minus sigma y, and sigma 3 minus sigma 1 can be plus minus sigma y. From where we get this value? Since tau max is sigma y by 2, so here we have sigma y by 2, and the maximum shear will be sigma 2 minus sigma 3 divided by 2. So 2 will be cancelled out and we have this expression. So these are the three possibilities, okay, for maximum shear stress if the stress is unordered. Okay. So I hope you are getting the point that the statement is tau max is equal to sigma y by 2, and we just apply this in the definition of tau max in such a way that any stress can be a maximum stress. Okay. So for two-dimensional system, we assume sigma 3 to be 0. Okay. So above equation becomes sigma 1 minus sigma 2 is equal to plus minus sigma y. Why plus and minus? Because it can be under tension or under compression. And as we discussed in the last video, that for even material generally the values are similar. Okay, so that's why we have related for tension or compression case. Similarly, when sigma 3 is 0, so sigma 2 is equal to plus minus sigma y, and sigma 1 is equal to plus minus sigma y. So if we want to plot these three equations, so sigma 2 is plus sigma y, okay, and minus sigma y. Similarly, sigma 1 is plus sigma y and minus sigma y. So on the axis of sigma 1 and sigma 2, if you want to plot these equations, okay, so sigma 2 is the vertical axis, sigma 1 is the horizontal axis. So if you want to plot sigma 2 plus minus sigma y, so sigma 2 plus minus, so this will be the value plus and minus. Similarly, if you want to plot sigma 1, so it will be sigma 1 positive and sigma 1 negative. Okay, so I hope you got these two things, and if you plot this sigma 1 minus sigma 2 plus sigma y or minus sigma y, you get these two lines. Okay, these two lines. So if we plot these three equations, we found that we have a hexagon. Okay, and that hexagon is known as Tresca hexagon or yield locus. Okay, or Tresca yield locus. Okay, so what does it mean? What does it show? What is it? Does it represent? It represents that for Tresca failure theory, the failure will occur if we are on the line or outside this hexagon. If we are inside this hexagon, we are safe. The material will not fail. Okay. So Tresca failure criteria when plotted gives us the hexagon in two-dimensional system. Okay. Now let's see for A point. At point A, which makes minus 45 degree, we can see it's minus 45 degree, with x-axis shear stress is equal to tau A, that is sigma y by 2. So here the value of stress, will be, shear stress will be sigma y by 2. Okay, so I hope you understand the Tresca criteria. So after plotting the Tresca, we got the yield locus in the form of hexagon, that is known as Tresca yield locus. So inside that yield locus we are safe, and outside or on the yield locus we have failure. Okay, that is we have reached the yield point. Okay, so I hope this criteria is clear. So we will try to discuss that in detail while we solve the numerical. Okay, so now just moving to the next failure theory, that is maximum distortion energy theory. This theory is also known as von Mises theory or octahedral shear stress theory. So we know this theory by the name of von Mises. So it states that yielding occurs when the distortional strain energy at a point equals to the distortional strain energy at yield under uniaxial tension on compression. It says that failure will occur or yielding will occur when the distortion strain energy is greater than the distortion strain energy under yield. Okay, so if distortion strain energy is more than the energy required to yield the material, the part will fail. Okay, so that's why this theory is known as maximum distortion energy theory. Okay, because it relate the distortion energy. Okay, so consider sigma 1, sigma 2, sigma 3 are the principal stresses, and epsilon 1, epsilon 2, epsilon 3 are the principal strains. So then total strain energy is given by, we know the formula, half sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. Okay, this is the formula for total strain energy. Now from Hooke's law, stress strain relationship are given by epsilon 1 is equal to sigma 1 upon E minus Poisson ratio upon E times sigma 2 plus sigma 3, and similarly epsilon 2 and similarly epsilon 3. We know these expressions and we discuss these expressions in chapter 2 strain. Okay, so now if we replace the definition of epsilon 1 in the formula of total strain energy, what we get? We get the total strain energy to be this formula, 1 upon 2 is sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 Poisson ratio times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Okay, this is just a simplification. We just substitute epsilon 1, epsilon 2, epsilon 3 in this expression and apply mathematical simplification. So we get the new and simplified form of total strain energy. That is this equation. Okay, and it's a very easy mathematics. If you try, you can solve it in 2 or 3 steps. So now we got the expression for total strain energy. Total stress is the sum of hydrostatic and deviatoric states of stress. So if you want to calculate total stress, is basically dependent on two things, hydrostatic and deviatoric. Okay, so energy stated with hydrostatic state of stress means sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to P, and we have discussed that this the similar concept in chapter 1. Okay, so we can write the hydrostatic state of stress as UH is equal to 3.2 1 minus 2 Poisson ratio E and P square. So from where we get that when we put in the total strain energy equation this expression, okay, and simplify, we got this definition of hydrostatic state of stress. So this is the energy for hydrostatic state of stress. Also, we know that sigma 1 plus sigma 2 plus sigma 3 is equal to 3p. So now if we use this expression and substitute that in above equation and simplify, so we get the transformed energy for hydrostatic state, that is UH will convert it into 1 minus 2 Poisson ratio divided by 6E sigma 1 plus sigma 2 plus sigma 3 whole square. And it's not very difficult simplification. Again, these require 1 or 2 steps. Okay, just we replace P from this expression and simplify, so we get this expression. So we have developed for the total strain energy and for hydrostatic state of stress. So if we subtract those two, we can determine the deviatoric state of stress, that is the distortion energy. Okay, hence strain energy for deviatoric state of stress can be determined by UD is equal to U total minus U hydrostatic. So we replace and simplify. So we get the deviatoric state of stress to be 1 plus Poisson ratio divided by 3 and sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. So this is nothing but just we put the definition of UT and we put the definition of UH and apply the simplification. So we get this expression for deviatoric state of stress or distortion energy. Now consider again the element for uniaxial tension that is subjected to yield. So we have sigma xx is equal to sigma y and all other normal stresses and shear stresses will be 0. So using Mohr circle we get this expression. So we have explained this calculation in the Tresca. So that's why we are not repeating that. We know that sigma 1 is equal to sigma y, sigma 2 will be 0 and sigma 3 will be 0. Okay, because we are using the biaxial state of uniaxial state of stress. Okay, so if we replace this definition of sigma 1 in and these definitions sigma 2 sigma 3 in UD, so sigma 2 sigma 3 terms will be 0 cancelled out and we simply get UD is equal to 1 plus Poisson ratio upon 3 sigma y square. Okay, so I hope we can simply get this expression by replacing sigma 1 to with sigma y. Okay, because all other values are 0. So we get now the expression for deviatoric or distortion energy. So now comparing deviatoric relations, we get now if we compare this expression with the previous one, this one, okay, and we compare if these two expressions and simplify. So this bracket will be cancelled out and we got this complete expression equal to sigma y square. Now if we simplify this expression further, what we get sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 2 times sigma y square. It's a simple simplification and rearranging this expression and taking the root, what we get 1 upon root 2 under root sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma whole square is equal to the sigma y. So this is the expression for three-dimensional system for von Mises failure. Okay, criteria. Now for plane stress condition sigma 3 is 0. So above expression will simplify it. Sigma 3 will be 0. Sigma 3 will be 0. So this expression becomes sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is equal to sigma y square. So this is the expression for von Mises failure criteria. And if you want to plot this expression, we know that it's the equation of ellipse. So above relation is an equation of ellipse which gives for plane stress condition an elliptical shape yield surface as shown in the following figure. So yield locus for von Mises will be an ellipse. Okay, so if we plot this, we simply get an ellipse. Okay, so yield locus for von Mises is an ellipse. So if we are inside this ellipse, we are safe. So or if we are on the edge or outside the ellipse, we have failed. The material is failed. Okay, now see particularly that point A. At A, sigma 1 is sigma. Here sigma 1 basically sigma and sigma 2 is minus sigma. Okay, we can see that sigma 1 is sigma and sigma 2 is minus. Okay, so if we replace these values in above expression and simplify, so we get sigma is equal to 1 upon root 3 sigma y. Okay, it's just a simple substitution. Okay, so sigma is equal to 1 upon root 3 sigma y, and if we determine the maximum shear stress at that particular point, that is sigma minus 0, so we get 1 upon root 3 sigma y. So this is the maximum shear stress at that particular point, 1 upon root 3 sigma y. So the important point for von Mises is that yield locus is for two-dimensional system is an ellipse. If we are inside the ellipse, we are safe. On the edge and outside, we have the material will fail. And this expression is the expression for the failure criteria for von Mises. So after that, we have discussed Tresca and von Mises. The next topic will be the comparison of these Tresca and von Mises. So comparison of Tresca and von Mises failure criteria tells that Tresca criteria is more conservative and gave 50% less yield surface area as shown in figure below. Now let's see the figure. Now for any particular case, for any stress state, if you plot if you use the Tresca criteria, you get this hexagon. And for the similar stresses, if you plot use the von Mises failure criteria, you get this ellipse. So this hexagon will always be inside the ellipse. Okay, so we have some space left between these two. That is amount for 15%. So Tresca criteria is more conservative, okay, as compared to von Mises. Okay, so you can see that hexagon will always reside inside the ellipse. Historically, Tresca was considered to be more fundamental of the two, but von Mises' form was seen as an appealing, mathematically convenient approximation to it. So now both are usually stated side by side with little or no preference. Okay, so this is the first statement that either you use Tresca or von Mises, both are same generally. But the Tresca theory is more conservative than the von Mises theory. So it predicts a narrower elastic region. The Tresca criteria can be safer from the design point of view because it's more conservative. But it could lead the engineer to take unnecessary measures to prevent an unlikely failure. But Tresca is conservative, but the thickness or the diameter, we will try to use more thickness. Okay, so this is one point that either Tresca is conservative, so should we use Tresca? Okay, the criteria choice depends on the type of design and personal understanding of the designer. So it's now based on the designer. Okay, either use Tresca and von Mises. So Tresca will gives it more safer, but it will use more material. Von Mises is less conservative, but it will save material. So depending on the choice of designer, so both of the failure criteria are generally used, unless it was identified or defined by the developer that you have to use Tresca or von Mises failure criteria. Now, the last point between the comparison is we have discussed the failure criteria or yield locus for Tresca and von Mises for two-dimensional system. But if we have a three-dimensional system, so we have the slant surface. So ellipse will be for Tresca, sorry, for von Mises, and hexagon will be for Tresca in three-dimensional system. Okay, and it's a complete slant surface. Okay, that is for Tresca we have hexagon that is having a length. Okay, length of Tresca will be there, but for von Mises we only have ellipse that is have the particular length in third dimension. So in three-dimension system, the von Mises is three-dimension ellipse, and for Tresca it's a three-dimensional hexagon. Okay, in a plane we have hexagon that has a particular length. Okay, so these are the two failure criteria for ductile material. So let's moving towards the third one. Third one is the strain energy density or total strain energy criteria. The strain energy density criteria proposed by Beltrami states that yielding occurs when the strain energy density at a point equals the strain energy density at yield in uniaxial tension and compression. So means whenever the total strain energy reaches the yield point, we have the failure. Okay, this is the simplified form of this statement. So total strain energy is given by this expression. So we have derived expression in the von Mises von Mises failure criteria. So just copying the similar total strain energy function. Now for a uniaxial case, we know that sigma 1 is equal to sigma y, sigma 2 and sigma 3 will be 0. So when we replace that in this expression, so we got the simplified form that the total strain energy will be 1 upon 2 e sigma y square. For by comparing both expression of ut for like this and that these two expressions, so we get sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 Poisson ratio times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3 is equal to the square of yield point sigma y square. Okay, so if you compare 1 upon 2 will be cancelled out and we get this expression. For plane stress condition, sigma 3 will be 0. So above equation simplified and gives following relationship. Sigma 1 square plus sigma 2 square minus 2 times Poisson ratio. Sigma 1 sigma 2 is equal to sigma y square. Now shape of yield surface of strain energy density criteria is an ellipse. In principal stress space that depends on the Poisson ratio. That depends on the Poisson ratio. For example, if we take Poisson ratio equals to 0, assuming a special case where Poisson ratio is 0, above equation become the equation of circle. Okay, so the yield locus will be circle for that. Okay, in case of Poisson ratio equal to 0, that is an approximation or assumption, because Poisson ratio can never be 0. Note, amongst three criterias, okay, of failure theories for ductile materials, Tresca and von Mises are mostly used to investigate the failure and stresses induced. Okay, so out of these three, von Mises and Tresca are mainly used. Okay, so with this, we completed the failure theory for ductile material. Now moving towards the failure criteria for brittle materials. As discussed earlier, for brittle materials, failure is initiated when material reaches the UTS value. The failure criteria for brittle materials are discussed below. We have maximum principal stress criteria. That is the first criteria that we are going to discuss. So it's simply name says suggest maximum principal stress. So we compare different stresses out of the three, and we have the failure criteria based on the maximum principal stress value. The criteria proposed by Rankine states that yielding occurs at a point when the maximum principal stress reaches the value equals to maximum principal stress at yield in uniaxial tension or compression. So whenever we have maximum principal stress value greater than the UTS value, then we have a failure. Okay. According to this theory, failure occurs when either maximum of sigma 1, sigma 2, sigma 3 is equal to sigma UTS. For plane stress condition, sigma 3 is 0. So Rankine theory can be rewritten as sigma 1 is equal to plus minus sigma UTS, or sigma 2 is equal to plus minus sigma UTS, depending on which one is greater. Generally, we have sigma 1 greater than sigma 2. So the expression will be sigma 1 is equal to plus minus sigma UTS. Now here it is very important to discuss plus minus sign and of UTS. Generally the brittle materials are good under compression, and they are not very much have not much strength in tender tension. So they are brittle materials are not generally the even materials. Okay, but if we study the failure, we should study sigma 1 is equal to the UTS under tension, and we also need to compare that with the compression. Okay, so we need to compare for both, because the brittle materials are not the even materials. So we have different values of UTS, and the difference is huge. Under tension the value is smaller, and under compression the value is higher, much higher. So maximum principal stress criteria for plane stress condition gives failure surface that represents a square. So now if we have plotted that, okay, assuming that UTS is same under tension and compression, so we get a square shape. But generally UTS is not the same. Criteria has good experimental verification, even though it assumes UTS is same in compression and tension. That is not the correct things to do for brittle material. Okay. For brittle materials, many other failure theories are present, but maximum principal stress criteria is mostly used because it's a simplified one, and it gives us better results. Okay, so with this, we discussed the first uh, failure criteria for brittle materials. Okay, and we found the yield locus, that is the failure region, will be a square if we assume UTS to be the same under tension and compression. So inside that yield locus we are safe. On the edge and outside the material will fail. Now the second failure criteria is maximum principal strain criteria. So previous was the maximum principal stress. Now the second is maximum principal strain criteria. It is also known as Saint Venant's criteria, states that yielding occurs when maximum principal strain equals to the maximum principal strain at yield under uniaxial tension or compression. So whenever maximum principal strain value is greater than the UTS value, the failure will occur. So principal strains are generally classified as epsilon 1 is greater than epsilon 2 is greater than epsilon 3. So in terms of principal stresses given by, so we know the stress strain relationship, epsilon 1, epsilon 2, epsilon 3 related with the stress in this term. Okay. So for uniaxial case at yield gives the following relationships. Epsilon 1 will be sigma 1 upon E because sigma 2 sigma 3 will be 0 for uniaxial case. So we have already derived that relationship. So sigma 1 will be equal to sigma UTS in order to have a failure. Okay. So because we compare the maximum principal strain and we assume epsilon 1 to be the maximum and we compare that with sigma UTS upon E. So for plane stress condition sigma 3 is 0. So above equations for epsilon 1 becomes sigma 1 minus Poisson ratio sigma 2 is equal to sigma UTS, or sigma 2 minus Poisson ratio times sigma 1 is equal to sigma UTS. So these are the two statements that we get from the stress strain relationship, and when we simplify that or when we plot that, what we get? We get this type of yield locus. Okay, so yield locus is somewhat like a rhombus. Okay, and inside that yield locus we are safe. On the edge and outside we have the failed material. Okay, so I hope you understand the mathematical derivation as well as the yield locus for maximum principal strain theory. Okay, now moving towards the third and the last failure theory that we are going to discuss, that is Moore's failure criteria. The Moore's theory of failure, also known as the Coulomb-Moore criteria or internal friction theory, is based on the famous Moore circle. Moore's theory is often used in predicting the failure of brittle materials. Along with principal stress, the Moore's failure criteria is also used. Moore's theory suggests that failure occurs when Moore's circle at a point in the body exceeds the envelope created by the two Moore circles for uniaxial tension and uniaxial compression. This envelope is shown in the figure below. Now you can see this figure in which blue circle is under compression because the brittle material is good, having good strength under compression. So when we plot that UTS, we got the larger circle, and if we plot under tension, we got a smaller circle. Okay, and then we have a dashed circle that is intermediate in between circle. Okay, the left circle is for uniaxial compression at the limiting compression stress of the material. Likewise, the right circle is for uniaxial tension at the limiting tension stress. The middle circle, that is dashed line, represents the maximum allowable stress for an intermediate stress state, means in between stress state. Now, equation for Moore's column failure criteria for plane stress condition is given by sigma 1 upon sigma UTS tensile minus sigma 2 upon sigma UTS compression. Means it compare both tensile strength under tension as well as under compression. Okay, so this is the statement for failure criteria for Moore's failure criteria, the mathematical equation or statement. Graphically, Moore's theory requires that the two principal stresses lie within the shaded zone depicted in the figure below. So we know that tension is smaller, compression is more. So we have this shape of the yield locus. So in tension we have a smaller region, but in compression we have larger regions. So when we combine and draw, we got this type of yield locus. So if inside that yield locus we are safe. Outside or on the edge, the material will fail. Okay, so this is the yield locus for the Moore's criteria or Moore's failure theory for brittle materials. So I hope you understand the three failure criteria for brittle materials. Now we will be solving few numericals for these failure criteria. So now see problem 1. When the loads that act on the hub of a flywheel reach their working values, the non-zero stress components at the critical point in the hub where yield is initiated are sigma xx is 100 megapascal, sigma yy is minus 14 megapascal, and tau xy is 50 megapascal. So up till now, it's given that this is the state of stress in such a way that yield has initiated, yielding has started, the material is filled. So the load stress strain are linear so that the factor of safety can be applied to either the loads or stress component. So this is very important statement. Generally factor of safety is calculated by the load, but if the relationship between stress strain and load deflection are linear, so we can determine the factor of safety using load as well as stress strain data. So the flywheel material has a yield strength equals to 300 megapascal. So this is the value of yield strength that is given to us. That is 300 megapascal. Now, assuming material follows Tresca yield criteria, we have to determine the factor of safety against yield. Okay. Similarly, the second part, assuming material follows von Mises failure criteria, and we have to determine the factor of safety against yield. Third one, determine which criteria is more conservative. So let's answer the third part, before solving this problem. We know that Tresca is more conservative. So the answer of C part is Tresca is more conservative. So we will prove this statement by mathematical calculations. So let's see the solution. Remember that we have been given sigma xx, sigma y, and tau xy, but the failure criteria is always use the principal stresses. So we need to convert these stresses into principal stresses by using Mohr circle equation, and then we need to relate that with the yield point. So the principal stresses are determined using equation for two-dimensional Mohr circle. So this is the expression. So when we replace the value of sigma xx, sigma y, and tau xy and simplify, we got these two values of principal stresses. Sigma 1 is 118.8 and sigma 2 is minus 32.8. It's a simple, simple calculation. So you can simply replace the values and you can got, this answer. Okay, now Tresca criteria. The failure criteria for Tresca says that maximum shear stress is equal to the yield, and we have proved this relation is sigma 1 minus sigma 2 is equal to sigma y. Okay, now this is the yield strength and this is the working stresses. Okay, now if we divide the failure by working, what we get? We get factor of safety. So yield strength divided by allowable, or that is working stresses, we get factor of safety. So when we divide sigma y by sigma 1 minus sigma 2 on both sides, we got 1, but not 1, we call that to be the factor of safety, because sigma y upon allowable is the formula of factor of safety. So now replacing the value of sigma y, that is 300, and sigma y minus sigma 2 118.8 minus minus 32.8, we get 151.6. So when we divide these two, we get 1.98. So by using Tresca criteria, the factor of safety comes out to be 1.98. It is important to note the statement of failure for Tresca is that maximum stress minus minimum stress is equal to the yield. Now moving towards the part B, that is von Mises failure criteria. For von Mises failure criteria, the statement is 1 upon root 2 under root sigma 1 minus sigma 2 whole square plus sigma 2 square plus sigma 1 square is equal to sigma y. So again, if we divide sigma y with this allowable stresses, we get the factor of safety. So factor of safety for von Mises will be yield strength divided by allowable, that is sigma y divided by this complete expression. So simply replacing the values of sigma y, sigma 1, sigma 2, so we get 300 and sigma 1 is 118.8 and sigma 2 is minus 32.8. So replace those values and simplify, we get this expression and we get the factor of safety to be 2.17. Okay, so among these two, the Tresca gives you the lesser value, so we use 1.98 as a factor of safety. And the answer of third, Tresca criteria is more conservative as it predicts yielding at smaller loads. Okay, so we can have lesser factor of safety, so Tresca is more conservative. So I hope you understand the utilization of Tresca and von Mises. Okay, so let's moving towards example number 2. A thin walled tube with closed ends is subjected to a maximum internal pressure of 35 megapascal in service. So it is the pressure that is given to us. And we have thin walled pressure vessel. The mean radius of the tube is 30 centimeter. Radius is given 30 centimeter. If the tensile yield strength is 700 megapascal, that yield strength is given, that is 700 megapascal. What minimum thickness must be specified to prevent yielding? Now, if you want to avoid yielding, what should be the minimum thickness? Now, consider failure based on Tresca criteria. It's given that the failure theory that we are going to use is Tresca. So, important is pressure is 35 megapascal is given. Radius of the tube is 30 centimeters given. The yield strength 7 megapascal is given. Okay, now this is the thin wall pressure vessel. And we know that we have hoop stresses, we have longitudinal stresses, and we have the third direction radial stresses. Okay, so since it's a thin pressure vessel, the radial stresses will be 0. So let's see the solution. So hoop stresses will be sigma 1, that is the maximum stresses PR upon T. Okay, we call it sigma max. And longitudinal stresses will be PR upon 2T. Okay, that is sigma 2 is equal to PR upon 2T. That is intermediate stresses. Okay, and the third one, the radial stresses will be sigma 3 equal to 0. Okay, because your thin pressure vessel thickness is very small, so we eliminate the third stress. Okay, we consider it to be a plane stress condition. So that sigma 3 is the sigma min. So based on Tresca criteria, the failure is sigma max minus sigma min is equal to sigma y. And we know sigma max is hoop stresses PR upon T minus sigma min is sigma 3 is equal to 0. So PR upon T minus 0 is equal to sigma y. And we know the pressure 35 megapascal, radius 30 centimeter. We need to calculate T, and sigma y we know 700 megapascal. So yield occurs when sigma 1 is 700 megapascal. So replace the values sigma y 700 megapascal, pressure 35, radius 30. So we can calculate for T. So T comes out to be 1.5 centimeter. Okay, so in order to avoid the failure, the thickness must be 1.5 centimeter minimum. Okay, based on Tresca criteria. I hope you understand the solution of the problem. Okay, so now let's move towards the third problem. A circular shaft of tensile strength 3350 megapascal, okay, is subjected to a combined state of loading defined by bending moment 8 kilonewton meter and torque 24 kilonewton meter. You see, we have solved first exam problem in which we understand the statement of Tresca and von Mises and how to convert that in factor of safety. In second, we use thin pressure vessel and using the concept of thin pressure vessel to calculate the thickness. Now here we have added the combined load now. We have moment as well as torque applied. Now we have to calculate the required shaft diameter D in order to achieve a factor of safety of 2. So it is given that factor of safety is 2 and we need to use Tresca criteria to determine the diameter. Okay. So this is the expression for combined load that we have torsion as well as moment. Okay. So how we are going to solve this problem? Since we have combined loading, and the method of solving this problem is that we deal these problems separately, first for torsion and then for moment. Okay, so we know that the flexure equation sigma upon y is equal to m upon I. Okay, and I we know that it is pi by 32 d4. So similarly sigma upon y, so when we replace y by d by 2 and simplify, we get sigma x is equal to 32 m upon pi d cube. So you have derived these type of relationship in your machine design or elements of machine design. Okay, and use this formula. But in exam, if this type of numerical comes, you have to start from the flexure formula, that is m upon I is equal to sigma upon y. Okay, and then you have to simplify to this expression. Similarly, if you use torsion equation, that is T upon J is equal to tau upon rho, and just replace rho by d by 2 and simplify, you get tau x by 2 with this expression. Okay, so in exam or in if this problem comes, you have to start from flexure formula and torsion equation, and then you have to come up with these formulas. So now you know sigma xx and tau xy, and sigma y will be 0. So now using Morse circle equation, if we substitute sigma xx equal to 32 m upon pi d cube and tau xy to be 16 t upon pi d cube and simplify, we can get the principal stresses. And you know that for failure criteria we need principal stresses. So sigma 1 comma 2 will be 32 m upon 2 pi d cube plus minus root this, and on simplification we get 16 upon pi d cube bracket m plus minus root m square plus t square. So these are two principal stresses that we get. And if we write sigma 1 minus sigma 2, okay, so we simply subtract. So what happened, this m will be cancelled out and we left only with 2 times root m square plus t square. So this 16 become 32. So sigma 1 minus sigma 2 will be 32 upon pi d cube root m square plus t square. Now important thing is why we are writing sigma 1 and sigma 2, because we are want to use Tresca criteria, and for Tresca criteria we need the difference of maximum minus minimum principal stresses. So that's why we have subtracted that. Okay, so now using the Tresca criteria, sigma 1 minus sigma 2 is equal to sigma y in terms of factor of safety. Sigma y upon sigma 1 minus sigma 2 is equal to factor of safety. So sigma y remains there, and just we put sigma 1 minus sigma 2 this expression here. So we get 32 root m square plus t square, and pi by d cube goes at the top. So we get this expression for factor of safety. Now here yield point is known, m is known, t is known, only d is not known, and factor of safety is 2 is given. So when we replace all those values, okay, and simplify, we get d. So d comes out to be 0.113 meter. Okay, so I hope you understand. First of all, we can determine the formula for sigma xx using the Flexible formula. Then we determine the formula for tau xy using Tognell equation. Then using Morse circle, we determine the principal stresses. And then we subtract principal stresses and then put in the formula factor of safety for Tresca. And then substituting the values and simplifying, we got dia to be 0.113 meter. Okay. Now consider that if the similar problem you have to solve using von Mises. So what will be the difference? If von Mises failure criteria is used, we have following relationship. So the failure or factor of safety will based on this formula. Okay, that is sigma y divided by this expression is equal to factor of safety. And when you replace sigma xx, so principal stresses sigma 1 and sigma 2, okay, these expressions, and in this expression and simplify, you get the factor of safety formula like this: sigma y pi d cube divided by 16 bracket root 4m square plus 3t square. Similarly, sigma 1 is the expression will remain same till this point, sigma 1 sigma 2, but instead of subtracting you have to put in this expression and simplify. After simplification you get the formula factor of safety like this, and after that you simply has to substitute the value of sigma y, m and t, and simplify, you get the diameter for von Mises. So I hope you understand this expression as well. So try to do this by yourself. Okay. Now moving towards the last numerical for plasticity. A foundation of a machine is made by grey cast iron. The most critical stress condition at a point in the part is shown below. Okay, so this is the expression under compression we have 20 kpsi, and so kpi is a wrong expression, it should be ksi, and 10 ksi under tension. So find the factor of safety in the foundation such that sigma uts is 25 ksi, under tension it's 25, and under compression it's 100 ksi. So failure criteria under tension and compression are given, because and it is UTS is given and grey cast iron given. So it's just basically a brittle material. So we use the maximum stress criteria for determining the factor of safety. The grey cast iron is brittle material. For solution we apply maximum principal stress theory. So sigma 1 is equal to plus minus sigma UTS. So means we have different values of stresses, so and also UTS are different, so we have two different factors of safety. So let's solve the problem. So maximum compressive stress in the part is 20 ksi. So from compressive stress point of view, sigma 1 is minus sigma UTS. Okay, so just divide sigma UTS by sigma 1. Okay, that is um, uh, failure divided by allowable. So we get factor of safety. So 100 is given and 20 is given. So both are negative. So negative will be cancelled out and we get factor of safety to be 5. Okay, so for under compression, we get factor of safety to be 5. Now, if we see tension, so maximum tensile stress in the part is 10 ksi. Okay, and from the compressive stress point of view, sigma 1 is sigma UTS. So for basically it should be tensile because we have already solved compressive, so it should be tensile. So this will be sigma 1 UTS. So just replacing sigma UTS under tension divided by sigma 1. So we got equal to factor of safety. So sigma yield strength under tension is 25, lesser as we know. Allowable is sigma 1 10. So when we divide, we got 2.5. So factor of safety comes out to be 2.5 under tension. So among these two, 2.5 and 5 values are basically we got. So amongst that we use 2.5 lesser because it's a more conservative value. Okay. So thus the factor of safety of the part will be smaller value, that is 2.5. Okay. So with this we completed the topic of plasticity. So we will try to discuss any query if you have in the live session uh, in the next week, inshallah. Okay, for so till then, take care. Allah Hafiz.